tree, and what we want to do is do depth first search, and then just print out or console log out, in case of JavaScript, console log out each node and its value. So depth search is you start at the root node, and you just want to go deep, so this way, not sideways, downward. So in this case, you go 8, 3, 1, 6, 4, 7, 10, 14, 13. That's depth search. I think that's like in order, it's called. You go left first, but as opposed to breadth search, where you go sideways, so it'd be 8, 3, 10, 1, 6. It's kind of like reading a book. 1, 6, 14, 4, 7, 13. And then you want to implement the JavaScript code. So we have our binary search tree class, and then we have a method called depth first search for each. And with the callback function, what you can ever do with that node that you're iterating over. We're going to use a recursive method. In this case, called in order, since in order is going left, left, right node. I'm pretty sure, yeah. So, and so what we want to do is essentially you just want to check if there's, since you're going left, if each node has a left child. So in this case, it does. So let's read it out. Read out 3, and does 3 have a left child? Yes. Does 1 have a left child? No. So then that means you go up to 6, which is kind of weird. I don't know how it quite works, how to go back up. But yeah, so that's what you're doing here. Is your binary search tree, is there a left child? Yes, then call in order again, and then call in order calls back. You call the callback function with the current new subtree. So when you go 8 to 3, you delete not delete all of them, but you just look at this new tree right here. This one I'm circling. I wish I could draw on it, but and then so then you just call the callback function, and it takes the value at that new node, so which would be 3. And you keep doing that until you can't do left, and then you do the same thing for right. So, and somehow it works out.